Hello good people, I am going to talk about electronegativity. What in the name of genetically enhanced cyberspace codes is it? In short, it is a measure of the relative attraction an atom has for the electrons in a covalent bond. Fantastic! But what does that mean? Let me bring in an example. So here I have a hydrogen and it is covalently bonded to a chlorine. Recall that a covalent bond, indicated by this line, means that two electrons are being shared between two nonmetals, in this case hydrogen and chlorine. However, it turns out that the sharing is not equal. Chlorine happens to pull on the electrons of the covalent bond more. Using more scientific language, we could say that the chlorine has a greater electronegativity than hydrogen. And it is always the atom with the greater electronegativity that will pull on the electrons of the covalent bond more. At this stage you might be thinking, well, that is great for you and all the other demented cauliflowers, but how am I supposed to know which atom has the greater electronegativity? Well, luckily we have a table for that. And here it is. The greater the value, the greater the electronegativity. In order to make things a little bit neater, I'm going to replace this table, one that contains only the main group elements. There are a couple of points that I would like to make about this table. So the first one, it was devised by Linus Pauling. Linus Pauling was an American chemist who was awarded 2 Nobel Prizes, one for his achievements in chemistry and the other one for his contribution to world peace by helping reduce the number of nuclear weapons that are around. His 2 Nobel Prizes certainly put my pride in my Tetris high score into perspective. Please note that the values on this table are unitless, and they have all been established or calculated relative to either hydrogen or fluorine or both. You might encounter electronegativity tables that have values that are slightly different to the ones shown here. The differences in values can also be the result of rounding. For example, on my table, the electronegativity of fluorine is given as 4.0. You might find some tables where it is given as 3.98. I have simply rounded the result to 1 decimal place. What do all of these values mean again? Well, as I have said earlier, the greater the electronegativity, the greater the pull on the electrons. So now I can compare the electronegativities of hydrogen and chlorine. Hydrogen has an electronegativity of 2.2, whereas chlorine has an electronegativity of 3.2. So based on these values, I can once again say that the chlorine is pulling on the electrons of the covalent bond more. There is one final point I would like to make, and it has to do with atomic trends within the periodic table. The smaller the atomic radius of an atom, the greater its pull on shared electrons. Recall that as we go across a period, or up a group, the atomic radius decreases. This in part is why fluorine is the most electronegative atom. So if you pair anything else with fluorine, the fluorine will pull on the electrons of the covalent bond more. Finally, you might be wondering about these 4 elements that have been left blank. Why is it that they do not have electronegativity values? In short, these are the noble gases that we cannot get to covalently bond to other elements. And because of that, we cannot calculate their electronegativity. You also might be wondering why it is that I'm talking to you about electronegativity. Well, electronegativity will help us talk about another concept called polarity, but I will leave that for another time. That is all for now, and I will see you on the flip side.